Okay, physics puzzles. You got a bunch of concepts, you got a method. Let's take this to another level. It's a puzzle. Lay the pieces out, follow the method. So we're going to do force puzzles here. See the physics. Sometimes it's tricky, so you're going to learn to retrain your intuition. But see the physics, use the method one step at a time. The method will draw you into the physics. And sometimes you have to retrain. You go, oh, I don't see this. So really good to do this. Let's take a look here. A few different cases. Here's one. Typical kinds of problems. Pushing an object, sliding it up a vertical wall. So this is pretty slippery here. And I might push it this way. You can think of an eraser in this case. And the analysis isn't bad. Again, one step at a time. So first step is choose your object, and I've drawn that in blue. Of course, that's my receiver, R, or name it whatever you want. And then I'm pushing with my hand, so I've modeled that with this green vector here. The wall is here, and so you know that when you look at it, choose an object, you're going to do a force analysis. You look for what's touching it. Clearly, my hand is touching it. F sub h is what I called it. And the wall is touching it. So the wall, as we said, any surfaces, including my hand, have a force from the grooves, contact force. That's our mechanical model. And that can be broken up into two parts. So certainly there's a part perpendicular. It's exerted here, but you can go over here and draw it this way. It doesn't matter so much. I'll just call that N, since there aren't lots of things going on here. And then, of course, there's the part parallel to the surface called friction. Now, I want to talk about that. A couple things. Yes, with your hand, as you change the angle that you push, you have more or less normal and more or less frictional force. So that varies. But we needn't overthink it. We can start to go here. What I want to look at here are some cases. So just realize in problems, on exams, etc., there's often multiple cases. And I want to look at what's the type and direction of the friction in all these cases. So suppose this object's about to slide up here, or it is sliding up. Let's have it sliding up. The thing is sliding up the surface. Do I know if the acceleration is 0 or not? Not by this. So it could accelerate up. It could be moving up and accelerating down, right? It could be decreasing speed, or it could be moving up at a constant speed. I'm not sure. But nonetheless, in this case, if it's sliding up, what kind of friction would I use? In fact, if you pause the video right now and try to answer that question, in what direction and what kind of friction is it in each of these cases? And can you say anything about the acceleration? Sliding up, about to slide up, a bit less of a push than part B, so it's not really about to slide up, about to slide down, and sliding down. So pause, fill that in, and now you're back. So sliding up. Well, if it's sliding up, then I should be able to see that I've got a force of friction downward. The surfaces, the R is sliding relative to the surface, so that's kinetic. And there is an equation. This is not a causality. The strength of that force, here's the direction. You can see it from the physics. And the strength is given by this kinetic coefficient of friction, mu k, or the roughness factor, and the amount that they're squeezed together. So you're doing two things as you push here. Notice that you are pushing into the wall and you are pushing up, which can be drawn. The components can be drawn anywhere at the tail or the tip. You can slide your vector up this way if you want, however you do it. Okay, fine. In this case, I don't know what the acceleration is. It's sliding up. I don't know. Let's see. Did I forget something? I think I did. There's a force here from contact, friction, and normal. There's my hand. And of course, there's the non-contact force. I'll just draw that right in here. Mass of the receiver times g. And of course we know that's true. So something I want to say in this case is Well, when I do my free body diagram, I just see what's touching and then I put it in the MG. Then I need to break it into components. So before I do that, I've got to choose my coordinate system. A coordinate system is like a grid. Now you can tilt that grid any which way. This can be positive, that can be positive, that can be positive, doesn't matter. But when you draw your coordinate system, put arrowheads to indicate the positive direction, whether you choose right or left as positive. In this case, it makes sense. We've got vertical here. So I'd say AY is equal to whatever. And then I've got a horizontal. It doesn't matter really which way. So I'll call that plus X horizontal. AX is 0 because it's moving along the surface. So that tells me that the horizontal forces must balance, right? So I've got a part of my force in, and the only thing here that could balance it is the normal. So that I should have an intuition for. The component of my force into the wall balances the normal force here. Whatever angle I have, I can get that. Suppose this angle is theta, and my force is FH. The component is adjacent to that angle, so FHX is the total strength reduced by this factor cosine theta, which is a number less than 1, right? And it's in the positive direction. So we've got that. And we can break that down. And then, of course, we'd have the vertical component being positive by my choice. The full strength reduced by this factor of sine theta. All right. And then I've got the mg down, so negative there. And then again, I've got the friction in this case. So if it's sliding, I've got this. If it's about to slide, what I've got is it's about to slide up, then the friction is down. But now it's Fk here, but Fs, or static, because it's not sliding. Max, now I'm going to tell you something, a little key little point that people mess up on. In that case, we do have an equation that is mu Sn. And in this case, super important point here, take Ay equal to 0. It's about to slide up. Don't let it slide. So you're right about to break or slip. Okay, now if it's a bit less of a push, still pushing up like that, you can have a downward force, but you have no equation. You just put it in as Fs. It's still static, not sliding. If it's about to slide down, then of course the grooves engage the other way. And if it's about to slide down, well, the wall's helping go this way, and I got Fs max, but the direction I can get from the physics, and that is a strength coefficient of static friction times the amount squeezed together, n. If it is sliding down, of course, I've got Fk, and we know that is Kn. Okay, fine. So there's one. So you have to pause and think, and if the case changes, that's it. So we've got that. Let's take a look at another puzzle. How about inclined planes or ramps? So those are very common. There's a variety of reasons why they're common, useful. A screw is a circular ramp, isn't it? Okay. So a big tip here is don't draw 45 degrees unless it is 45 degrees. Make sure that you draw one angle bigger and one angle smaller, and that makes it a lot easier to track down your angles. So for example, here's a block or some sort of thing on an inclined surface here. First I need to choose my object. Clearly it's the blue one in this case, R. And I will put in the forces. So the only thing touching is, in this case, the surface. Of course, we know that the surface is going to exert a force right here. We often draw it up here, fine, but not vertical. That is a mistake that I see sometimes. So it's perpendicular. One way to do this is put your finger along the surface and your thumb is perpendicular. And that's the direction of the normal. Away, certainly it's not grabbing it this way. So there's the normal, you got that. And then I've got friction, possibly. Now again, it's a little tricky, as we said before. Is the friction this way or this way? Friction, and what kind? So it depends on the cases. There's a lot of cases that you have. One case would be, at what angle can you incline it just before it slides. What angle is it just before it slides? So maybe that's theta max just before it slides. But again, it could be moving up, it could be moving down, it could be accelerating, it could not be accelerating. All those cases, think physics and you put it in. Now in terms of forces, there's only one more force and you know what that is. There is the force of gravity. So the next step then is, I'm done with my free body diagram, then I need to choose coordinates. And it depends on the situation. You're going to see different cases where it's useful. For instance, I can make my coordinates this way, and maybe I'll have the positive up. Okay, I'm going to go ahead and put some arrows on there to make that good, and arrows just to make it clear. All right, I've chosen that. But now I can orient this various ways. Now if I orient it this way, it's kind of nice because mg is all in the negative direction, negative y direction. However, this vector is somewhat in the x and somewhat in the y, the friction. And the normal would have components as well. And that's fine, but if this is going to accelerate, it's going to accelerate along the plane. And since it's going to accelerate along the plane, if it's free, then it's going to have an acceleration this way. So what I like to do is call it either plus or minus. That way I kind of like this, plus x. Ax is equal to a plus y. Ay is equal to 0. Now if you attach it to a string over a pulley, it might accelerate up the plane. Fine. Now one little bit that people have trouble seeing is how to get the components. If I choose it this way, which is a very common choice, if I choose it this way, it's not always this way, so remember there are going to be other cases, then how do I get the components? Because clearly n is in the plus y direction and friction is either in the plus x or minus x direction. But I've got to break this down into parts because now my coordinate system is not like this. I actually have to flip it and my positive this way and that way. And then I've got to put it on top, put this grid on top here of my vectors. So let me kind of clean this up a little bit and talk about that. And let's do that real quickly. So draw your pictures. If it's too hard to see, redraw it. You'll learn from that. So don't shortcut, right? Shortcuts, no good athlete or musician shortcuts, they don't get good that way. So draw it nice and big, nice and clear. I'm going to try to make that really big. It doesn't have to. Now the length represents the strength of the force, right? Not a length. So there's my M of my receiver G. That's the strength of the force. But how much is it going in my x and y directions? Well, again, draw a grid. So I will draw a grid. Lines parallel to y, not very parallel, through the tail and the tip. That, kind of like that. And they don't have to be beautiful. Lines parallel to x through the tail and the tip. And you should have a box. And that box shows you the components of mg in the y direction. And the components, I like dashed lines with an arrow. Make sure you put an arrow on your components. Let's make sure that's clear that I'm going in the negative y direction and in this case, positive x direction. How much is it? Well, if this angle here is theta, let's try to make this really clear. All right, I've got this. Angle is theta. Hey, wait a minute. If that's theta, I know this is vertical and horizontal, so that's 90 degrees. And that angle is the complementary angle, or 90 minus theta. Okay? So in other words, I can just think if that's 30, that's got to be 60. If that's 20, that's got to be 70 or anything. Well, that angle is also the same as this angle here, isn't it? All right, cool. So that angle is the same. That's 30, that's 60. That would also be 60. But my coordinates are perpendicular. So if that's 60, and this is 90, or this is 90, if that's 60, this one here would be 30, or the comp. So that angle is the same as that angle, isn't it? As is that angle. So these are the things you know. That's theta. And so the force of gravity in the x direction, which can be drawn either way, is the force of gravity. It's opposite that angle, which is the same as that angle, so I'll use the sine theta. Notice that you don't always use cosine theta for the x direction. Just look at your triangle. You know, that's a bad mistake. It's also in the positive direction, so I'm going to go ahead and emphasize that so I don't mess that up, right? And then I go over here and I say, well, how much is it in the y direction? Oh, the force of gravity in the y direction is the total strength, mRg. But wait a minute. Negative. I just look, and I'm thinking physics, so I've got good bookkeeping, and it is adjacent. This side is adjacent to that angle, which is the same as that angle, so it's cosine theta. And so when I put my forces in, I just think about what's touching an mg. I choose a coordinate that's going to be nice, so usually that's where acceleration is all in one direction and no acceleration. Then the sum of the forces in the y is 0, and the sum of the forces in the x is max. I take all my forces, put them in a table, break them into components. Sum of the force x equals max, sum of the force y in this case equals 0, and then I solve and put in the details. So let's take a look on the next little video about some little subtleties with strings and ropes. They're kind of cool.